Okay, this is section 8.4, trigonometric identities. In the previous sections, the Pythagorean identity, remember that sine squared theta plus cosine squared theta equals 1 was developed. And we know that this is an identity because essentially the left side is always equal to the right side no matter what value you plug in for the theta. So if there was something that was conditional, an equation just in general, something like 2 parentheses x minus 3 equals 5, that's only true if you actually distribute the 2 and solve for x, which ends up being 11 over 2. So if it's only true for specific pieces, like sine x equals 0, that's only true for certain values of x. So if we don't have the possibility of all solutions being true in an equation, then it's just a regular equation. But if every possible theta that you plug in is true for that specific situation, that's when you know you have an identity. So two functions f and g are said to be identically equal if f equals g for every value of x for which both functions are defined. Such an equation is referred to as an identity, and if it's not an identity, remember, it's a conditional equation. So just to remind ourselves of some of the identities that we have learned so far this semester. Tangent of theta is sine theta over cosine theta. Cotangent of theta is cosine theta over sine theta. The reciprocal identities, cosecant theta is 1 over sine theta. Secant theta is 1 over cosine theta. And cotangent theta is 1 over tangent theta. The Pythagorean identity, we know the first one is sine squared plus cosine squared theta equals 1. If you divide everything by cosine squared, you get tangent squared theta plus 1 equals secant theta squared. And if you divided everything by sine, you get 1 plus cotangent squared theta equals cosecant squared theta. So those are our three versions of the Pythagorean identities. We also learned that certain trig functions were either even or odd. The only even group was the cosines and the secant family. So what that means is it doesn't matter if you plug in a negative of theta, it is also going to be the same answer as the positive of that theta. Okay, and we learned that sine, tangent, cosecant, and cotangent were all odd. So when you plug in a negative of a theta, essentially, then it changes the sign theta to the opposite value. And the same is true for all the others. Now that just has to do with what kind of symmetry these graphs have. So the goal in this section is going to be establishing new identities by algebraic manipulation strategies. So we're going to look at some different techniques. Now, the biggest thing you have to realize when you are working with an identity or trying to manipulate something is that we have to use the properties that we know are true, or we can use algebraic tricks that we learned. Especially if you're trying to verify what an identity is, you have to start with one side of the equation, which we don't have an equation yet in number 1, and you have to work with that until you make it look like the second side. So we're not really solving, we're manipulating. So let's look at this first one. If you multiply by something that is equivalent to 1, that will sometimes help you clean up an expression. Now, the thing I like to remind people of is back in college algebra, so in 136, if you had things like 2 over 1 plus the square root of 3, we were not allowed to leave the square root of 3 in the denominator. And because this is a binomial, we can't just multiply by square root of 3. That will get rid of this one, but it will add a square root of 3 onto the 1. So we use something called the conjugate. The conjugate is the same two terms, but a sign in the middle is different. And whatever you do to the bottom of a fraction, you do to the top. The whole point of that is when you FOIL out the bottom, you get no square roots left. We can do a similar process here to try to see what we can combine and get rid of, maybe. So I'm going to use the conjugate of this statement, which is 1 minus cosine theta. If you multiply by that on top and bottom, you've really multiplied by 1. So what that gives me is, I'm going to leave this undistributed for a second. So this is sine theta and 1 minus cosine theta. I'll show you why I leave it undistributed and just because you never know what might cancel when you do this. So when we FOIL out this bottom, we get 1 minus cosine theta plus cosine theta minus cosine squared theta. So that's me just FOILing that out. In the middle, those cancel. So I get 1 minus cosine squared theta. And then remember our Pythagorean identity, sometimes I'll write these over here to the side to see so you can see what I'm using. If we were to subtract cosine squared over, 1 minus cosine squared theta is actually sine squared theta. And then we can reduce one of the signs out. So this would be 1 minus cosine theta over sine theta, because one of these signs can cancel with one of those. Now, we could continue if we wanted to. So this is one way to end this if we don't know where the ending is. We now know that sine theta over 1 plus cosine theta is the same thing as 1 minus cosine theta over sine theta. If we wanted to continue, because like I said, we don't know where to stop, we could break this up into two separate fractions. 1 over sine theta minus cosine theta over sine theta. Notice they both have the same denominator. And then that would be cosecant theta minus cotangent theta. So see, these identities can be stopped in multiple formats or states. It just depends on what they're trying to have us prove. So right now we're just practicing using techniques to kind of manipulate. Okay, so for example 2, it says use algebra to simplify the trigonometric expression. We could rewrite an expression over a common denominator. So if we wanted to get a common denominator for this statement right here, we would need to think, okay, they're different because one's a plus and one's a minus, so we would need both of these to be part of our common denominator. All right, so we multiply by what's missing, so this side's missing the 1 plus sine theta. Whatever you do to the bottom, you must do to the top. This one's missing the 1 minus sine theta. We work out our top of each fraction, so this would be 1 plus sine theta over, if we wanted to go ahead and multiply that denominator out, that's 1 minus sine squared theta, by the way, if I FOILed that out. Be careful not to get too happy. You can't cancel any of this because there's adding and subtracting between them. You can only cancel when there's multiplication between two pieces. Okay, and then if we add across the top, 1 plus 1 is 2. And we still have our common denominator because the sine theta and the negative sine theta cancel each other out. And if we wanted to go even further, we could use the Pythagorean identity again to realize that that is cosine squared theta. So that is one place where we could stop. Example 3, we could try factoring. So again, just showing you different methods to how we could work some of this out. I think with the top here, I could try to use perfect squares. This would be 1 plus cosine theta and 1 minus cosine theta. Because remember, we've already practiced that a couple times. That's what that would FOIL back out to. On this one, I could pull a sine, or these are V's. Let me fix that. You do want to stay consistent with the variable, or my math lab won't like you. So this would be sine V, and then we'd have a 1 plus cosine V because we pulled that out as a GCF. And doing that was helpful because we got this. So 1 minus cosine V over sine V. And again, if we wanted to go further, we could split this up. They didn't specify where to stop. So this is cosecant V minus cotangent V. That's exactly the same thing we got for example 1, which means that the part we started with in example 1 is synonymous or equal to this part. So that's just anytime you get the same answer at the end, once you've simplified, then those two expressions would be equal to each other. All right, so now we're going to show you how to establish an identity. Now, when we work on an identity, you only work on one side of the actual equation. We are not solving. We're not dividing by things on both sides. We're not adding or subtracting something over. We are trying to force the left side to be manipulated into the right side. So for this first one, we have sine theta times cotangent theta plus tangent theta. The first thing I would try is maybe let's distribute this. So this would be sine theta cotangent theta plus sine theta tangent theta. Usually if I have anything other than sines and cosines, I try to turn those into sines and cosines because that sometimes makes things easier. So this would be sine of theta. Cotangent is cosine theta over sine theta. So that's going to cancel out my sines in a minute. Plus I still have my sine theta. Tangent is sine theta over cosine theta. So for this first one, those cancel and I'm just left with cosine of theta. For this one, I'm left with sine squared theta over cosine theta. Okay? And then notice that we can multiply cosine theta over 1, if you kind of want to think of it that way, by a cosine theta over cosine theta. What that's going to do is give us a common denominator. So anytime you have a fractional part and a non-fractional part, you want to see if you can put them together, especially if you have a single thing on the other side. So that would make that cosine squared theta over cosine theta plus sine squared theta over cosine theta. And because of the Pythagorean identity, sine squared plus cosine squared, those are both positive, equals 1 over cosine theta, and 1 over cosine theta is secant theta. So I have verified that that identity is true. But notice, I never did anything with the secant on the other side. You are just leaving it alone. Okay, so let's look at example 5. It says establish the identity cosecant theta minus cotangent theta equals sine theta over 1 plus cosine theta. This time I'm going to, again, you could choose to just leave the left side alone and work with the right, or you can choose to leave the right side alone and work with the left. We've already shown a couple of times that a few things equaled cosecant theta minus cotangent theta, so maybe I'll go backwards this time. So I'm going to leave the sine theta over 1 plus cosine theta alone. So for this first thing here, I might try to change these into sines and cosines. So cosecant would be 1 over sine theta minus cotangent is, remember, cosine theta over sine theta. So that at least gives us the same denominator. So remember, we're leaving the right side alone. Now I can combine this, and I have sine theta, and on top I have 1 minus cosine theta. Now, before we said that we could get rid of something in a denominator by multiplying by its conjugate. You can also do the same thing when you're trying to get rid of a binomial in a numerator, or at least make it look different. I can multiply by the conjugate again because that will clear out some of the stuff that's going on top. So just because it's not in the denominator doesn't mean you can't still use this trick. So what that would give me is, this is still going to be the same. I'm going to leave this as undistributed, so sine theta 1 plus cosine theta. On the top, we get 1 minus cosine squared theta, because remember you would FOIL that out, but the middle terms cancel. That makes the top sine squared theta because of the Pythagorean identity. And we're about one step away because now I have a sine and a sine on top that can cancel, but I still have a sine left over in the top. So notice I have verified that the left side can be turned into the right side. Okay, and then the final example for 8.4, we want to establish this identity that sine squared theta minus tangent theta over cosine squared theta minus cotangent theta equals tan squared theta. I'm going to leave the tan squared theta alone. There's not many places I could go backwards from that that would make this very easy except using Pythagorean identity. So what I'm going to do is I'm going to look at converting all of the things that are not sine or cosine into sine or cosines first. So this would be sine squared, and there are other ways probably to approach this. This is just my go-to. So that would make this sine theta over cosine theta for that tangent, and this guy's over 1. On the bottom I have cosine squared theta over 1 minus, this would be cosine theta over sine theta. Now, if you want to get rid of little fractions within a big fraction, if you can find an LCD for all of them, which is a sine and a cosine, we can clear that out. So I'm going to multiply both top and bottom by a sine theta and a cosine theta. And I don't have to do anything to the other side. First of all, we're not supposed to be, but because I'm doing this to top and bottom of that big fraction. Okay, so if I distribute this, this would be a sine cubed theta cosine theta for the first fraction. For the second part, the cosines would cancel, but I would still have a sine squared, because sine times sine. On the bottom, I would get sine theta cosine times cosine squared is cosine cubed theta. And then when I multiply to the second fraction, the sines will cancel, but the cosines will not. So you'll have cosine squared. Now, why that's a little bit helpful is I can pull out a sine theta on top, because they have that in common. That would leave me with sine theta cosine theta minus 1. Oh, I'm going to pull out a sine squared. Sorry, they both have at least 2. And then on the bottom I can pull out at least a cosine squared theta. That would leave me with a sine theta cosine theta minus 1. And notice that this is a match, so we get sine squared theta over cosine squared theta equals tan squared theta, and sine over cosine is tangent, and since they're both squared, it is tan squared theta as well. So, I mean, that's not the only way I could have approached this one, but it's using the trick of turning everything that's not a sine or a cosine into a sine or cosine, trying to work with simplifying the fractions that you're given. This case I had to clear little denominators out of the top and bottom, and then always try factoring if you can. So this is a good viewing of examples for what you should be expected to know how to do. And that is the end of 8.4.